Hi y'all, welcome to section 2.2, limits from a graphing perspective. So here's the verbal definition of limit. L is the limit of f of x as x approaches c, if and only if L is the one number you can keep f of x arbitrarily close to just by keeping x close enough to c, but not equal to c. So I know that's just a lot of words, and the good thing is, hopefully by the end of the chapter, you should be comfortable with that. So the idea is here is if we have x and f of x, okay, and we have some value of c. So c is some specific x value. As long as we approach c from the left, we're getting closer and closer to a certain value. And as we approach c from the right, we're getting closer and closer to some value. It doesn't actually matter what's happening at c, it just matters what's happening as we get closer and closer to c. As long as these two values are approaching the same point, whatever value that would be, we would call that L, the limit. Whether there's a hole there or whether there's a dot there, it's not going to matter as long as you're getting closer and closer to one single value as you get closer to C. Then we'll have a limit. So we'll be looking at just one example of that today. And you'll be using your fingers actually a lot whenever you do problems like this. Okay. So in order to do limit problems, we have to be really clear on the concept of zero, and undefined, and indeterminate. So 0, remember if we have 0 divided by something, that's okay. We get 0. If we have something divided by 0, that's when you get an undefined, or does not exist, because it's not okay to divide by 0. Don't forget the cute little okay and no. So an indeterminate case is when we have 0 divided by 0. We cannot determine which rule it's going to follow. Is it going to follow this rule that says that 0 divided by anything will always be 0? Or is it going to follow this rule that says that anything divided by 0 will always be undefined? Indeterminate. We cannot determine what the answer is going to be. So your instructions for these type of problems will be, you need to do something else. Okay? Most of our examples in this chapter will be that you need to use algebra, like factoring, to simplify. Okay? So this lecture is all about this one example. And this one example is you are driving off from a traffic light. Your distance d of t in feet from where you started is given by this equation here, 3t squared, where t is in time, in seconds, since you started. So d of t is here, and that's in terms of feet, and t is here, and that's in terms of seconds. Okay. So we're going to sketch d of t versus t, and hopefully we're clear this is a nice up parabola, something along those lines. Okay, it's just slightly wider than a normal parabola because of the 3. Slightly steeper than the regular parabola because of the 3. And we are going to be looking at this big question. How fast are you going 4 seconds after you started? Okay, so we only care about the starting point here at 0 and beyond. And we're going to be specifically looking at 4. So let's go ahead and draw our graph just so we can make sure we have 4 in there. And 1, 2, 3, 4, something along those lines. Okay. But remember, this is just d of t and t. Okay. So if I figured out what that value is right there, okay, d of 4, I want you to think about what that would represent and calculate it. Okay. So hopefully we're clear that at d of 4, we would have 48, okay, which would represent that after 4 seconds, she has traveled 48 feet. Okay? That does not answer the question, how fast are you going 4 seconds after you started, or she, or whomever. That would be approximated by drawing in the tangent line here at 4 and looking at the slope of that tangent line. Okay? This activity we're going to do today will not be an approximation, it will be the exact value of how fast you were going at 4 seconds. So what we're going to be doing next is writing m of t, which will be standing for the average speed, as an algebraic fraction from the time interval from 4 seconds to any t seconds, where t is greater than 4. So we're coming over here and just randomly saying, all right, here's some t value. I want to look at the rate of change between those 2 points. So 4, 48, t, we have nothing better to call it than d of t. Okay. I'm going to say that the slope between those 2 points, so if I connect the blue dot and the green dot, that the red line, that's a pretty good approximation for this green tangent line that I've drawn in. Okay? And where limit will come into play is as t is getting closer and closer to 4, hopefully you can imagine that that line here would be getting closer and closer to the actual slope of that tangent line. Okay, so we'll be taking the limit as t gets closer to 4 of this expression m of t. Okay. So again, the average speed from 4 to t seconds, we call this m of t, and that would just be taking the slope between those 2 points. So that was d of t minus d of 4. I'll just go ahead and call it d of 4 for now, over t minus 4. Now we have actually calculated d of 4. Remember that was 48. So I know that that guy is going to be 48. Okay, t minus 4. And remember they told us what d of t equaled. D of t was that equation, that 3t squared. So you will have to use your equation in this case. Okay. And so that's what m of t equals. M of t equals this stuff. Okay? So that would be the average speed from 4 to t seconds. Now if we looked at this right now and I asked you what m of 4 equaled, if I tried to plug in 4 here and tried to plug in 4 here, hopefully you would see that we get 0 over 0, this indeterminate form. Okay? Which means we could not use this equation to figure out exactly how fast she was going, or we were going, at t equals 4. So our something else that we're going to do here is to factor and reduce m of t as much as possible. But all the while, hopefully realizing that t cannot equal 4 to get plugged into this equation. So we're going to factor here that 3t squared, 3 times t squared minus 16 up top, over t minus 4. And then this t squared minus 16 will break down to t plus 4 and t minus 4. All over t minus 4. And we can see if those t minus 4's would cancel. So we are left with, I'm going to go ahead and distribute that so I see the nice linear relationship, 3t plus 12. And this is what m of t equaled. Okay. But it's super important, if you're going to state that m of t equals this stuff, you need to make sure you're stating the restriction. M of t will equal this stuff as long as t does not equal 4. Okay? You should always include that in your statement if you are just simplifying an expression like this. Okay? I think that's all we need to do for that part. Yes. Okay, so then for part B, it's saying that we want to see a sketch of what m of t would look like. Okay? Make sure we include that point of 4. Well, if m of t is a nice linear equation, m of t was 3t plus 12, as long as t didn't equal 4, okay, realize we'll just have a nice linear equation, a nice line, but at 4 we're going to have a hole. Okay? So I'm going to go ahead and just roughly sketch this. I'm going to start here at 12. I'm going to go up 3 to the right 1, up 3 to the right 1, up 3 to the right 1, and we have something along these lines. 1, 2, 3. But here at 4, we need to remember that t could not equal 4. So we're really dramatic about that. And here at 4, we'll draw an open circle showing that that value is not included in m of t. Okay. So letter C says your speed at the instance that t equals 4 is the limit of your average speed as t approaches 4. So your actual speed will be the limit. So we'll write L-I-M, standing for limit, of your average speed. Remember, we called the average speed m of t. So we're taking the limit of m of t, okay, as t approaches 4. As t approaches 4. And whatever this thing equals will be the actual speed we were traveling at after 4 seconds. Okay. So this is where we get our fingers out and start looking as t gets closer and closer to 4 from both the left and the right. Okay? So here's along your t-axis, we're getting closer and closer to 4. We take those fingers and bring them up to the function, and we're trying to get closer and closer to 4 along my function and seeing if my fingers are getting closer and closer to one single value. If they are, whatever's sitting over here is your limit. Okay? So I know the hole versus not having a hole might be kind of distracting, but if you refer back to the verbal definition of limit, remember it said it didn't matter what was happening right at C, only what's happening as you get closer and closer to C. So for this problem, 4 is our C value. We're getting closer and closer to 4. My fingers are getting closer and closer to this hole. And wherever that hole should have been, I know that that guy will be my limit. Okay? So how can I figure out where that hole should have been? Is by plugging in the restricted value into the equation. So if I plug in 4 here, 3 times 4 plus 12, we got 12 plus 12, which gives us 24. So I know that that output right there would have been 24. Okay. And so that means the limit of m of t as t approaches 4 equals 24. Okay. If we look at the, that was the first question, what does the limit appear to equal, was 24. Excuse me. What are your units of this limit? Well, the units of a limit problem will just be the units of whatever you are taking the limit of. So let's go back and think about what the units of m of t were. Remember that m of t was the difference of the t value plugged into the distance equation minus the 4 value plugged into the distance equation over t minus 4. So if we just look at the units here, these were distance values, which were feet, and these were time values, which were seconds. So our units for the limits must be feet per second. Okay. So hopefully that makes sense, that that is the actual speed we were traveling at. After 4 seconds of traveling, we were going 24 feet per second. Okay. And realize that all of that we just did right now was kind of the long way, using the definition of derivative, at the point specifically for 4. Now there will be a shortcut, okay? And I know those of you that took AG Calc last year learned the power rule. You don't need to be responsible for it yet. But I do want to show you that a problem like that can be done within a few steps, okay? We could get the exact speed we were traveling at after 4 seconds by using something called the power rule, which is good for polynomial functions. I could take this 2, pop it out in front as a coefficient, and then I'm going to decrease my exponent by 1. And this will give me the derivative for every value of t along that distance equation. So I could plug in 4 and get 6 times 4, which is 24. And again, the units here would be feet per second. This is just a preview of the power rule. You're not responsible for it yet, but we will be learning that in Chapter 3. Okay? So please whisk this information, and I look forward to discussing it with you in class tomorrow.